Good afternoon, my fabulous chemistry students. Polar versus nonpolar compounds is the subject of today's video number 9. When we are done, we can tell the difference, of course, between a polar and a nonpolar compound. All right. What are the major differences between polar and nonpolar compounds? Well, the difference in electronegativity is going to make the electrons, right? Because electronegativity is how bad do I want an electron? If I have one atom that is a much higher electronegativity, he's going to take the electrons away from the other. Now, even if they're sharing in something like that's covalent, he's still going to share unequally this way. And this ends up giving us a different shape. So the shape is not symmetrical. We call that asymmetrical. Basically, really what this boils down to as far as a compound or a molecule goes is, are the electrons evenly distributed or not? Okay, so polar versus nonpolar notes. Okay, a molecule is covalently bonded always has two or more nonmetals bonded together. We call molecular or covalent. Okay, so just a little bit of a recap of covalent notes. Polar molecules are asymmetrical. They have an unequal sharing of electrons, or I could say there's an unequal distribution of electrons. They're not all uniformly dispersed around the atom. Okay. Um, if I have a lone pair of electrons, like in, let's say, nitrogen's famous for this. Let me see if I can draw nitrogen. Why are you not drawing down there? There you are. Okay, so there's nitrogen. I got this lone pair up here. So when I bond in here with like my H's will bond right in there like that, put my puzzle together. This lone pair is going to make it uneven, okay? So there's a lone pair around the central molecule. That's a dead giveaway that I do not have what's called symmetry. So what do we do down here? And you see these arrows here that go up and across. What I'm looking to do is, if I go like this, am I the same on both sides? Well, right now you'd say yes, right? Because I have an H here and an H here. And it's not showing up when I do that, but that's okay. When I go across this way, though, am I the same on both sides? I have a lone pair of electrons up top and an H down here, so I'm not the same. So that's asymmetrical, okay? So we can do it for H2O and HCl and do the test. If I do HCl, and I say, I got H with one lone electron, and then I got Cl with its 7 valence electrons. This is my bond. Now, just looking at it, are there as many electrons on the left-hand side as the right-hand side? No. And does it fail this, or does it pass the symmetry test? When I cut it this way, is the top the same as the bottom? Well, yeah. But if I cut it this way, is the right-hand side the same as the left-hand side? No. So that gives us a key. Water. Okay, let's do water real quick. Of course, HCl is asymmetrical, and it's actually, you can see that all the electrons are around one side, not the other. Okay, so let's see. Oxygen. 1, 2, 3, 4, 5, 6. I'm going to put in a hydrogen here and a hydrogen here. When I cut it across this way, is it the same on both sides? When I cut it across this way, is it the same on both sides? Both answers are no in this regard. And I do see the lone pair, so that is another telltale sign that I will be a polar molecule. There is a difference between polar and nonpolar bonds and molecules. Kids get it mixed up all the time. Right now, we're only talking about molecules, or compounds. Symmetrical molecules means there's an equal sharing of electrons. It's symmetrical. It's the same on all sides, okay? There will, of course, be no lone pairs around the central atom. Cl2, let's go ahead and do Cl2. See, I got chlorine with 1, 2, 3, 4, 5. I'm going to do 6, 7 on this side because I just know I want to put the other chlorine over here on the right of it. So I got a Cl, 1, 2, 3, 4, 5, 6, 7. Now, in this case, are there the same amount of electrons around this chlorine as there are around this chlorine? And the answer is yes. So let's go ahead and do the symmetry test. I'm going to draw a line this way. Is it the same on the left hand and the right side, other than color, of course, Mr. Milks? Yes, the same. I say the same atoms and the same number of electrons. And if I cut it this way, is it the same up and down? Yeah, I have the same kind of atoms, same number of electrons. So this is what we call symmetrical. It's the same on all sides. All right, so we have some more for you to practice. I have CO2 and I have CCl4. All right, let me see. I think that, yeah, so I'm just going to go ahead and do these real quick because CO2 is a kind of a, nah, it's not a pain in the butt, but I don't want you to think it's a trick, okay? Let's do C is my central atom, carbon. One, you know, 1, 2, 3, 4 electrons. Then I have oxygen, and oxygen has 1, 2, 3, 4, 5, 6 valence electrons. I'm going to do this oxygen in red also. 1, 2, 3, 4, 5, 6 valence electrons. So I need to take a red and a green and bond them together, and a red and a green and bond them together, and a red and a green and bond them together, and a red and a green and bond them together. Do you see how many bonds we made total? Okay, now I'm going to stick with the green. That's going to look something like this. C, double bonded to an O, double bonded to an O. I have my lone pairs, but the key with these lone pairs are they are not on the central atom, they're on the outside atoms. Okay, when I cut it this way, is it the same on both sides? The answer would be yes. If I cut it this way, is it the same on both sides? The answer is yes. So this one would be symmetrical. Okay, CCl4. Right, see, so here it is. Right, there are often polar bonds inside nonpolar molecules. Okay, so here's a case where CCl might be a polar bond. So I'm going to do carbon, 1, 2, 3, 4. And I'm going to have some CLs. Cl, 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 Cl. And I'm not done. I got to put in chlorine's electrons. I know how many they have. I'm going to kind of bypass the rules a little bit just to make this part faster. As far as the one on the, first two together, one at a time around the bus. I know you can get mad at me if you want. I know. It'll be okay. The difference between Monica and me is we know when and when not to break the rules. So I've cut this one down the middle. Is it the same on both sides? Yes. If I cut it across the middle, is it the same on both sides? Yes, it is symmetrical. Therefore, it is a non-polar molecule. Can have polar bonds, but this is not that there's a difference between a polar bond and a polar molecule. And polar molecule is the shape of the whole thing. Are my electrons evenly distributed? And if we go back to this one, actually, you can see that around all the chlorines, there's all sorts of electrons. So I have a whole group of electrons down here, an equal group here, an equal group here, and an equal group here, and they all kind of cancel out. Right, so this one down here weighs good with this one, and this one matches with this one, and everything matches just fine, and that's what we call symmetrical. So you can do practice packets, pages 37 through 39. We're almost done with this thing, thank goodness. And now we know the difference between a polar molecule and a non-polar molecule. I'll see you guys tomorrow in class.